All right, well, hey, welcome to week 3 of calculus. Can't believe that we're already in week 3. We're already a sixth of the way done with this class. Whoa. But welcome to a short week. Hopefully everybody had a good Monday without class. But anyway, so welcome back. So today our plan is to continue doing what we were doing, right? We're starting to work on different techniques for integration, and we were kind of in the middle of, well, almost done with substitution. So I'm going to do just a couple more substitutions to kind of remind you. And then we're going to start looking at other forms, other functions that we can integrate to start kind of rounding out our list, right? Like how do we deal with exponential functions and logarithmic functions and all the other things that we've kind of seen along the way. So that's my goal. But of course, before we start, I want to open this up to any questions on homework. I know that the next set of homeworks are due tonight at midnight. So are there any that we'd like to look at?
Can we look at substitution question 10?
All right, I got that. Thanks for that, Tim. Any others? All right, so Chase wants number 14, also from substitution. Okay, I'll put that on there. Okay, sounds good. So, so errors, is that also from 1.5? Yeah, okay. All right, so I've got numbers 7, 10, and 14 all from the substitution section. So let me go ahead and share that screen and we will take a look at them.
10 messed me up a bunch of times and I realized I was forgetting to type plus C because all the other ones have it automatic.
Yeah, that might actually be the issue with number 10, but let's take a look at it. Yeah, you got to be really careful and pay a lot of attention to what exactly they want you to put in and what pieces are missing, because that happens all the time, where it'll be something like, you know, where it'll say write it as a %, but then sometimes they have the % symbol in there, sometimes they don't, and you know, so let's go take a peek at them. So 7, 10, and 14. All right, so we've got for, well, where did 12 come from? Let's go back to 7. All right, so here's 7. So consider this definite integral. So mine looks like x times the 4th root of x squared plus 6. So it can be transformed into a basic integral by letting u equal. All right, so what's it look like we should do here for our u? What would you want to let u equal in this case?
X squared plus 6.
Yeah, let's try the stuff that's in that square root. So I would go with x squared plus 6. Except my computer is not letting me actually click in there. Oh, don't do this to me, computer. Oh, yay. Google Chrome is not responding. Okay, well, let's at least talk this through. So I would definitely let u equal x squared plus 6. So then what's the du going to equal? What's the derivative of x squared plus 6?
2x.
It's just going to be 2x, right? So then we're actually looking pretty good, because if you look at that du equals, okay, I do not know what my computer is doing. Hold on a second. I'm going to stop sharing so you don't see all this nonsense, first of all. All right, so clearly it's going to be one of those days. Because now I'm even getting the wheel of death on my stop share. Right. Okay, so I just stole sharing into my phone here. So, oh. All right, I think I'm back. All right, so you guys can all see me. We're all good. All right. Let's see if we can try this again. I'm not going to bother with the whiteboard, or at least I'm going to stay away from my Google Chrome for a second as I try to salvage this. So for that one, actually, let me see if I can go to a whiteboard here. If not, we'll go back up to the actual whiteboard. Yeah, I'm going to go back up to the actual whiteboard because my computer's being funky. So hold on one second here, guys. I'm going to switch. I'll be right back. All right, apologize for the technical difficulties, but it's clearly one of those days. All right, so for this one, we are looking at the integral, and I think it was this. So we saw that the way to accomplish this is to start by letting u equal x squared plus 6. So then du is equal to 2x dx. So if we start substituting stuff in here, we'll still have an x, and then we're going to have a fourth root of u. And then the dx is equal to du over 2x. Right? If I just solve this thing for dx, I get dx is equal to du over 2x. So I'm trying to color code it here. All of the x's, the original, are in blue. The u's are in orange. But the good news is we've got an x divided by an x. So what we're going to be left with is the integral of 1/2 the fourth root of u du. And this one now we're going to be able to integrate because this is just u to the 1/4, and we can use power rule. So I think if I remember correctly for the boxes, you're going to want to put this into box number 1, so x squared plus 6. You're going to want to put 2x into the second box because if you look at it, it's a du equals box times dx, right? So the dx was already there, so we just need the 2x. And then it says, so I would turn it into this what integral, and I think it was integral with a box. And so I think you need to type in this, although I'm not 100% sure if the du was outside the box or not. And I'm not going to touch my Chrome because I'm afraid it's going to cause an epic collapse.
I think it was. I just put like 1/2 u to the 1/4 power, and that worked.
Okay, so the du must be outside the box. All right. So this would be the substitution then to make this one work. So this one's not even asking us to actually do the integral. It's just what are the steps we need to set it up. All right, so is that okay for this one? All right, so I apologize, my computer is trying to do something here. All right, it looks like I've got control of my computer again, so I'm going to go and look at the other problems. So the next one was number 10. Let me see what that looks like. I'm not going to share it, but I'll go ahead and write it up on the board. So this one, we've got the integral of, for me, it was dx over 4x plus 9 squared. So yours will look similar to this, hopefully. All right, so in terms of a substitution, probably our best guess or best choice is if we let that 4x plus 9 be our u. So let's see what happens if we do that. So we'll let u equal 4x plus 9. So du is equal to 4 dx. So if I substitute stuff in, the dx is du divided by 4, 1/4 du. And then the 4x plus 9 squared is u squared. So we're integrating 1/4 1 over u squared. So that substitution is going to bring us here. And now this one does ask us to go all the way through. So think of this as u to the minus 2. So we're going to get 1/4 u to the minus 1 over -1. And of course, because this is a indefinite integral, since there are not bounds, we do need to plug on the plus c. So this is minus 1 over 4u plus c. But if you try to put that into the box, it's going to give you the red X of shame. Because what do we still need to do? What's the last step we need to do in this case?
Sub back u.
Yeah, we got to put that u back in. So we'll replace this back with the 4x plus 9. So we get minus 1 over 4 times 4x plus 9 plus c. And I think that was Rigney who was talking about he was having trouble until he realized the plus c. Yeah, this one definitely wants a plus c because there is no plus c already in the box. So in terms of the substitution, the u equals would put in the 4x plus 9. And then for our final answer, it should look like this guy down here in kind of the red. All right, so okay for that one, better for that one. All right, so then let's look at number 14. Oh, that's a good one. All right, so this guy, we're integrating, at least my number 14, looks like the integral of 4 sine squared s times cosine of s ds. All right. I know it's weird having a variable s, But if you don't like it as an S, make it an X. It's all good. Just remember when you put it back in, put it as a variable S. But this is another one where we're going to want to do a substitution. Now, I don't know if you remember this, but on Friday, we actually did the integral of tangent using a substitution. And the reason I'm bringing that one up is because for tangent, we did a u equals cosine. And when you've got sines and cosines, you definitely want to use one of them as your u, because the other one's going to show up in the du. So the question here is, which one do we want to actually be u? Do we want it to be sine or do we want it to be cosine? Well, I mean, it doesn't really matter. We can probably make it work either way. But here's what I do to decide. I look at this and I think about which piece is more complicated, the part with the sine or the cosine. Well, clearly the sine bit's more complicated because there's the sine squared. So that's what I'm going to pick for my u. I'm going to let u equal sine squared. Or sorry, sine. So if we'll let u equal sine of s, then du is equal to cosine of s ds. So notice that this entire cosine of s ds is there in my du. So I'm going to be able to replace that entire thing with a du. So this integral then is going to look like 4u squared, right? Sine squared, and sine is now u, times du. So it's especially nice if when you look at this integral, you've got just one of those trig functions times the dx, or in this case, the ds. Because then that's going to get lumped into your du if you let the other function be u. So we get 4u squared du. This is going to be a quick integral then. This is going to give us 4u cubed over 3 plus c. But of course, we do need to substitute back. And when we do that, we get 4/3 sine cubed s plus c. And something I definitely suggest here when you're entering it in, make use of parentheses. Be really careful with your parentheses. Because of the sine cubed s, it needs to be sine of s, right? Sine of s cubed. So make sure that the preview box looks right, that you're cubing the sine and not the s. So I don't know if that was the issue or not, but something to watch out for. Also, make sure you put the plus c because it's not in the box. Right, it's not already there. All right, so better for these guys, 7, 10, and 14. Yep, okay, good.
Thank you.
Yeah, you're welcome. All right, so there you go. So don't forget to get in there and finish that homework tonight. I think the last section that's due is 1.5, the section on substitution. All right, so let's go ahead and move forward. Let's keep going. Let's keep doing this, do these integration things to help us see what's going on. But I want to go back and look at, remind you about using substitution for the trig functions, right? We already did tangent. Let's do cotangent, just to kind of remind you how that worked. And then we'll look at like what the integral of secant is, and then kind of go from there. All right, so this trick with cotangent is very similar to what we did last time with tangent. So this should kind of look familiar. So let's just say we're going to look at the integral of cotangent of x dx. So like I mentioned last time, when you're in a situation where you have no other idea of what to do, when you've got trig functions, a good idea is to turn them into sines and cosines. So if we do that here, cotangent is cosine over sine. And so what we can do for this one is very much what we did with this, the last homework example you guys just asked me about. I can let u equal sine of x, so then du is equal to cosine of x dx. So everything on top here, the cosine x dx, is now going to be a du. And so this turns into du over u, which we're now ready to integrate. So this is going to end up giving us the natural log of u. Technically, we do need absolute values around those. So I'm going to go ahead and put that there. Plus c. And of course, we now need to replace our u. And so we end up with the natural log of the absolute value of sine of x. So it's a nice little trick. Gets us the integral of cotangent. So this is the function whose derivative is cotangent. It's the natural log of sine. So let me go ahead and put up on the board here, just so we can kind of keep track of where we were. We've now seen the integral of tangent. If you go back and you look, that was the natural log of secant of x. And now we have the integral of cotangent equals the natural log of sine of x. And before anybody yells at me, I'm going to put plus c's on there. All right. So we now have integrals of those two functions. And it may be at about this time you go, well, this is weird now. When we differentiated, the derivatives were all really similar. We just changed some signs. All of a sudden now these integrals, they don't look like that anymore. Right? One's the natural log of secant, the other is the natural log of sine. But it turns out, let me just show you that pattern still kind of holds. Like, because what you might have been wanting to do, and I think I mentioned this last time, that the integral of cotangent, you can actually still follow that same pattern and make it the negative natural log of cosecant of x. And I want you to see that these are actually exactly the same. That negative out front, that's a -1. We could bring that in as a power. So this would be the natural log of cosecant to the -1. And of course, 1 over cosecant is the natural log of sine. So we're still seeing that same pattern with the antiderivatives, with the integrals, that we're getting the same thing, just with the cofunction and change the sign. It's just because of the rules of logs and the properties of the trig functions, we can change that into just natural log of sine, which we would rather have than the negative natural log of the cosecant. Anyway, but there you go. So now we've got integrals of tangent and cotangent. We also know the integrals of sine and cosine. Those are kind of basic, which leaves two more we got to do. We got to get the natural logs of secant, secant and cosecant. So for completeness, let's get secant. And now you're not going to like this one. Not because it's ugly per se. I mean, it's a little bit ugly. But you're not going to like this because it requires a miracle step. And for those of you who aren't aware what a miracle step is, those are the steps in the proof where something just shows up and you go, okay, where the hell did that come from? And the answer is, it's a miracle. the math god smiled upon whoever it was at the time and said, hey, put this in there. Why? Because it's going to work. Okay, right? Miracle step. So there's going to be a miracle step here, which you're not going to really like. But before we go there, I just kind of want to show you something that popped up in this integral that also showed up in the integral of tangent. That's also going to show up in the integral of secant and cosecant. And I want you to look at what we had after we did the substitution, right? We do this substitution and we ended up with this integral right here. We had integral of du over u. And if you go back and you look at your notes, or if you go back and watch the video from the other day, you'll see that when we did tangent, the same thing showed up. We got another du over u. And when we integrated that, that gave us natural log. So hopefully you remember this, that if we have a function that was natural log of u, we found that y prime was equal to u prime over u. Natural logs were really nice to differentiate. They always had the same form. What was inside the natural log went into the bottom, and its derivative went on top. Well, notice this form, du over u, that's u prime over u. And so always, when you end up with this form, du over u, you're going to get natural log of u plus c. So this is something you want to look for. With antiderivatives, if you ever end up with a fraction, if your antiderivative, if the function you're trying to integrate is a fraction, look and see if the derivative of the bottom is on top. Because if it is, it's fast. It's a natural log. All right, anyway, I just wanted to point that out because we've run into it twice, and we're going to run into it again when we do secant. All right, so let's do secant. So at this point, you're probably figuring out how this always plays out. If we're going to do the integral of secant, we probably want to turn it into sines and cosines. So let's do that. Let's make it 1 over cosine dx. And so then we're going to see if we can do a substitution here. All right, so if you're going to do a substitution, what would you let u equal?
Cosine x.
All right, so that probably sounds about right. Thanks, Mariella. So let's try cosine of x. I mean, it's really our only choice. It's the only thing we've got. So if we let u equal cosine, like we like to do, then du is going to equal a negative sine of x dx. And so if we try to substitute all this stuff in, we're going to get 1 over u. Cool. But the dx is going to be a minus du over sine of x. And notice that that sine of x, we can't get rid of it. It's still in there. And unlike before when we've done u substitutions, all the x's were able to go away. We were able to simplify it down. So now all of a sudden, that's a horrible choice for you. Right? It's not going to work. So we go, well, crap. What else can we do? So I saw Stephanie put in the chat box. She said, well, what about u equals 1 over cosine of x? Meaning, what if we just started at the beginning and said u equals secant? Oh, that's interesting. Let's see what happens if we do that instead. So this clearly doesn't work. So let's just try again. What if we let u equal secant? All right, so what's the derivative of secant? Anyone remember?
Secant tangent.
It's secant times tangent, good. So this is secant times tangent. So if we do the same kind of thing to substitute, well, the secant becomes a u, but now that dx is going to be du over secant tangent. Well, at least that secant we can replace with another u, right? Since u is equal to secant, we can put that in there. So we end up with the integral of u du over u times tangent. Well, okay, cool, these u's cancel, but we're still in the same problem where we've got a du and an x. Okay, so we've really tried the two things that we could in terms of doing a substitution. Right, when we went to 1 over cosine, we tried u equals cosine, didn't work. No. And we tried, well, what about just the plain old secant? Didn't work. All right, so we're kind of stuck, right? But now here come the trumpets from above, announcing the presence of the math gods coming down to shine their light upon us and give us the inspiration to do this. So somebody saw this. Who it was, I don't know. I lost the history. But somebody recognized this as the trick. Here's what we're going to do. I'm going to take this secant and I'm going to multiply it by a fraction. And that fraction is going to hold the same thing on top and bottom. So I'm really multiplying by 1. And here's what I'm going to multiply by. I'm going to take this secant of x. And I'm going to multiply it. Just go with this. By secant plus tangent over secant plus tangent. Because all of this is just a glorified version of 1. So looking at that, I know you're going, oh yeah, that makes total sense. All right, so where'd this come from? Inspiration. It came from fiddling around and playing around. But check this out. This is actually really beautiful. If we do this, this now gives us the integral of secant squared x plus secant x tangent x. And before I even go to the bottom, I want you to recognize that these are derivatives of trig functions, right? Secant squared and secant tangent, those are the two derivatives that involve secant. Now, if we go to the bottom, we still have secant plus tangent. But this ugly, horrible looking thing is still the same as just secant. But here's where the magic comes in. Now, let's let that bottom be u. So I'm going to let u equal secant plus tangent. If I differentiate that, the derivative of secant is secant tangent, and the derivative of tangent is secant squared. Wait a minute, that's the stuff on the top. So all of this that equals my du. So this turns this integral into du over u. All right, so again, miracle step. Seeing this, multiplying by secant plus tangent on top and bottom. But it does turn it into a form that when we do substitution becomes just du over u, which means its integral is just going to be a natural log. So we get natural log of u plus c, of course. And if we replace the u back in, we get that this integral is the natural log of secant plus tangent plus c. So was I right? You didn't like this one? That miracle step seems to come out of nowhere. Well, we're standing on the backs of giants, right? There have been centuries of people doing calculus before us. And so we get to make use of their inspiration. And now we know how to integrate secant of x. All right, well, let me go ahead and put that up on our chart here as an integral of secant. So the integral of secant of x is equal to the natural log of secant plus tangent. Plus c, just to make everybody happy. Well, okay then. All right, well, so the trick for cosecant is really kind of the same. You just multiply by cosecant plus cotangent, because then that's going to give you a cosecant squared and a cosecant cotangent, which were the derivatives off by a sign. And so if you end up doing cosecant, it looks very similar. It's just it's the negative natural log of cosecant plus cotangent. All right, well, there you go. You now have all of the integrals for all 6 of the trig functions. Sine and cosine were nice. They were easy. Tangent and cotangent, not terrible. Secant, cosecant, seem like they come out of left field, but this is their antiderivative. But they all came back to that du over u form. So I want you to watch for that, because that's going to end up giving us natural log. And it shows up a lot. I mean, it shows up a ton with all kinds of functions. So let me just show you some more where we get that du over u form. All right, and in fact, that's so big, I want to just put this over here real quick. That the integral of du over u is the natural log of u. All right, so be on the lookout for this guy. So, for example, here's another place where we'll see that. How about we're anti-differentiating 2 over 3x minus 4. Well, this is going to be one where we will do substitution. And we're going to let u just be the bottom of this fraction. Let's let u equal 3x minus 4. So then du is equal to 3 dx. So that means when I replace my dx, I'm going to get du over 3. But this is going to now be the integral of 2/3 du over u. So just look at where all these pieces came from. The 2, of course, is still the 2. This 3 came from the du piece. The du replaces the dx, and the bottom becomes u. So this is 2/3 du over u, which is 2/3 natural log of u. And if we replace it back, we end up with 2/3 natural log of 3x minus 4 plus c. Boom, done. So fun fact, if you ever have a fraction whose denominator is linear, so mx plus b, right, like this guy, then its integral is going to be a natural log of that denominator. It just will have potentially a constant multiplier on it. Right. So it's nice. It's really easy to recognize those things. And after you do a few of them, you'll start seeing the patterns. Right. So here's another one. Let's say we've got the integral of 1 over x plus 4. All right, well, it's going to be the natural log of x plus 4 plus c. And I know there is no constant multiple because if I differentiate this, x plus 4, I get 1. So I just get it. So this can be quick. Once you do a dozen of these, 20 of these, you'll see the pattern, excuse me, and you won't even think about it anymore. You'll go, oh, I've got a linear on the bottom. Boom, I'm done. In fact, how about Bruce will help you out here. Let me show you what the pattern is and what it always looks like. We'll do it generically. Let's do a generic linear. All right, so we're going to do an integral of 1 over mx plus b. So insert your favorite line there. So u is going to equal mx plus b. So du is going to equal m dx. The m is a constant multiple, so it goes along for the ride. The derivative of x is 1. And then the b is a constant being added, so it just goes away. So dx is equal to du over m. So if I replace all this stuff, I get 1 over m times the integral of du over u, which is 1 over m times the natural log of u. So we end up with the natural log of mx plus b divided by m. So my laziness just came through. It came out and said, hey, let's just do a line and see what happens. So now anytime you got 1 over a linear function, its integral is the natural log of that line divided by the slope. Done. So kind of interesting that these natural logs start showing up with rational functions, right? If it's such that the derivative of the bottom is on top, so that you can replace it out, you're going to get a natural log. Kind of cool. And even sometimes rational functions that don't look like they're just 1 over or a constant over a linear will turn into that. So let me show you this trick because this will come about as well. And I'm just going to warn you, this is going to bring back some algebra from the past that you're probably not a huge fan of, but no, what are you going to do? All right, so let's say we're going to look at the integral of 3x cubed minus 4x squared plus x plus 2 divided by x minus 3. All right, so you see that integral and you probably just threw up a little in your mouth. And you heard me say just a minute ago, yeah, it doesn't look like it, but it's going to turn out nice. This actually turns out really nice to integrate. It's going to be crazy easy. but we got to do a little bit of algebra first. So what we're going to do is we're actually going to do polynomial long division. So I know you've seen this before. Well, I don't know you've seen it before, but you should have seen it before. And it's a trick that we play all the time. You may remember last quarter, in first quarter calculus, when we were talking about limits to infinity and asymptotes, we used polynomial long division to find the slant or oblique asymptotes. So this is another place where we use that long division. Well, let me do it over here. Let's get it set up here where we're going to take our x minus 3 and we're going to divide it into 3x cubed minus 4x squared plus x plus 2. So 3 goes into 3x cubed, 3x squared times. So that gives me 3x cubed minus 9x squared. Subtracting that off, x cubes go away, minus 4 minus a negative 9 is a positive 5x squared. Bring the rest of the stuff down, and I just keep going. X into 5x squared is 5x. So 5x squared minus 15x. Subtracting that off, x squareds go away. I get 1 minus a negative 15, which is plus 15. So that's 16x plus 2. And one more step is to add the 16. So I get 16x minus 48. Subtracting that off leaves me 50. And I stop because now that constant x isn't going to go into it. So what that lets me do is rewrite this as 3x squared plus 5x plus 16 plus 50 over x minus 3. So these two are identical. They don't look it. I freely admit that. But they are equivalent mathematically. And if you look at this guy, this is going to be pretty easy to integrate. So before I do the integral, any questions on my polynomial long division? And I just realized I put the quotient in the glare of the light. I apologize there. So this should say it's 3x squared plus 5x plus 16. Okay, so there's the algebra. Now let's do the calculus. So the 3x cubed, or sorry, 3x squared, its integral is x cubed. The 5x gives me 5x squared over 2. The 16 gives me 16x. And then the 50 over x minus 3 is going to give me 50 natural logs of x minus 3. The 50 is a constant multiple. And 1 over x minus 3, it's a line. So I get natural log of x minus 3 divided by its slope. Well, slope is 1. And then, of course, we'll finish it off by putting a plus c. So the integral of that fraction we had at the start is actually right here. So you can see how quick the integral actually was once we got it into that form. And this is going to happen to you a lot, where a little bit of algebra, sometimes not just a little bit, you might argue that this isn't a little bit of algebra, but just some, how about we'll just go with some algebra. By doing some algebra, you can convert into a form that you know how to integrate. This is going to be a recurring theme with integration. All right, when we do other techniques later, like, for example, trig substitution, I think I may have mentioned that there's a type of integral where we use trig substitution as a technique. That technique, same deal. We're going to do substitution, and then we're going to use our trig knowledge to turn it into a form that we can integrate. Right? But this polynomial long division is a big one. When you've got rational functions, that's a good place to start, because then it often leads it into a turns it into a form that's pretty easy to integrate. All right, so how we doing? You liking this form? du over u? That's kind of handy. All right. But we still don't know about the integral of natural log, right? Like this form led to natural log, but the question is, what do we get when we actually integrate natural log? So, what is this? What if we just have a function, natural log? All right, now, unfortunately, we as a group are not ready to find this. So I'm going to tell you what it is. I'm not going to prove it yet, though, because we don't have the skills yet to prove it or to see where it comes from. So this is going to feel a little bit like a miracle. It's just because you haven't seen it yet, but we'll be there not too long. When we get to the technique integration by parts, I'll show you where this comes from. But the integral of natural log, and yeah, get ready, it's equal to x times the natural log of x minus x. So I'm going to go ahead and put a box around that, because boxes mean remember this. But the integral of natural log of x, the antiderivative, is x log x minus x. Okay, so like I said, I'm not going to prove to you where this came from. I'm not going to show you where this comes from. But we can actually prove that this is correct. How can we see that this actually is the antiderivative? What can we do? What do we know how to do to see that this actually is the antiderivative?
Do an integral.
Derive it.
Yeah, how about we just take its derivative? If we take the derivative of this, we should get the natural log. Because that's the whole point, right? This is the antiderivative. So let's just do that. Let's take a derivative of x log x minus x. So this first part, we need the product rule. So we need the derivative of the first one times the second. So we get 1 times natural log plus the derivative of the second one times the first. So it's going to be x times 1 over x. So that was the product rule for x log x. And then minus x, its derivative is just minus 1. So this is natural log of x plus 1 minus 1, because the x times 1 over x is 1. And of course, 1 minus 1 is 0. This equals natural log of x. All right, so cool. We know for sure that the antiderivative of the natural log of x is x log x minus x. Okay, cool. We got it. To me, it's still a little bit like it feels like a hollow victory. You know what I mean? We got the antiderivative. Yeah, but it just sort of like showed up. I'll show you later. You'll see why it must be x log x minus x. But like I said, we're not quite ready for that just yet. But have you noticed something? Have you noticed now how integrals of like really kind of nice basic functions, they're getting kind of ugly. Right? Go back to tangent. Tangent's integral was the natural log of the secant of x. Right? The integral of natural log is x times natural log of x minus x. And you're going to see that. You're going to see that. A lot of real basic functions, their antiderivatives get ugly looking. They get kind of gnarly. And that's because when we differentiated, we didn't get just nice functions, right? And so going backwards, same kind of thing is going to apply. All right, well, cool. We now have the integral of natural log of x. What if it's a different base? What if it's like log base 2 of x or log base 10 of x or something like that? It'd probably be good to get a formula for that as well. But that's pretty easy to do, knowing the natural log, because we can do this. Let's go with log base a. We're going to integrate log base a of x. So insert your favorite base. So here's what we're going to do. We're going to turn it back into natural log. We're going to use the change of base formula. Which says you can turn it into any other base. I'm going to pick natural log, but I'm going to do this. All right. So again, how did I go from here to here? This is the change of base. So go back and look at your pre-calc stuff from the logs section, and you'll see, you can go see where this comes from. But what's beautiful about this is that natural log of a is a constant. So I can actually pull that out front. And we know that when you do a constant times an integral, you just get that constant times its antiderivative. So this is going to look like the integral of log base a of x. It equals that x log x minus x, but divided by natural log of a. So we're just taking that same antiderivative for natural log, and we're dividing it by natural log of a. So let's go ahead and put that in a box as well. But there are your integrals for any log. And in fact, this one in orange that I boxed in orange, that's the only one you need to know, because natural log, that's just base e. And if you put an e in here, natural log of e is just equal to 1. So the first one was a general case of this second one. This one's a little bit more broad. All right, cool. Now you know antiderivatives of all 6 trig functions and logarithms. Let's keep going. Now that we've got logs, what about exponentials? What are the antiderivatives of those? But before I go there, any questions on the logs? I know that it doesn't sit well, but are we good so far? All right, well, let's tackle exponentials now. So let's start with e to the x. Our good friend, we like this guy. What about e to the x? All right, so can you think of a function whose derivative is e to the x?
Isn't it also e to x?
Is it? What makes you think that, Susanna?
Or I think that's the antiderivative.
Okay, well then that would mean that the derivative of e to the x
is e to the x.
Yeah, of course it is. This one's going to be e to the x plus c. E to the x, we love it because its derivative is itself. Well, if it's its own derivative, it's its own integral. Beautiful. So when it comes to exponentials, we like exponentials. The integral of e to the x is just plain old e to the x. Boom, done. Nothing more to do. All right. So that's cool. We love e to the x's. And even if we get things that are not just e to the x, we still like them in general because they are things that turn into e to the x when we do substitutions. So for example, what if we had, I don't know, the integral of 2x e to the x squared dx. No, let's just make it x e to the x squared dx. So you see the e to a power and you get a little bit excited because you're like, nice, I know what to do with those. But since it's not just x, this is one where we'd need to do a substitution. So obviously the best choice in terms of substitution idea, something to integrate, would be if this was e to the u. So let's let u equal x squared. So then du is equal to 2x dx. And replacing these x's with u's turns this into 1/2 e to the u du. So the half is going to come from when we substitute in for the dx. Right, we're off by that constant multiple. All right, well, 1/2 e to the u. Man, talk about easy. The 1/2's a constant multiple, so it sticks around. E to the u, its antiderivative is e to the u. So 1/2 e to the u, its integral is 1/2 e to the u. Oh my God, you're going to love these. Because anytime you have a constant multiple of an exponential function, its integral is itself. Like, oh my God, they're so beautiful. Well, of course, we do have to replace our u again. Ooh, whoop-de-doo. But that last step then brings us to 1/2 e to the x squared plus c. So there is the antiderivative of x e to the x squared. It's 1/2 e to the x squared. All right, so you're going to like running into e's. In general, they're kind of nice. Obviously, you need to be able to convert it into a form that we know how to do using substitution, which isn't always the case. Like, I just want to be very clear that you'll run into plenty of integrals where you can't do what we just did. I don't even have to change this one much for it to be a problem. Because what if all I did was drop that x out front? I'm going to get rid of that x. Let's just look at the integral of e to the x squared. Right? So okay, cool. That's an e to the thing. We're going to be all good. So you try doing the u substitution like we just did. You let u equal x squared. So du is equal to 2x dx. And if we try to do that whole substitution stuff, we're going to get e to the u times du over 2x. And the problem is we didn't get rid of all of the x's. And even if we tried using the u substitution thing, it's going to turn it into u's that lead to just the same kind of problems that we had before. Right? So just because you've got e to a power doesn't mean it's nice. That's going to be quick and easy. Yes, the ones I'm showing you are, because we're just starting out, right? It's like if you know, it's kind of like the whole swimming kind of thing. If all you're ever doing is standing in water up to your knees, like, this is easy, and I throw you into the ocean, not so easy, right? And that's kind of where we are now. But just realize that sometimes e to a power isn't so nice. In fact, it's a little fun fact for you. This integral right here, e to the x squared dx, it's actually impossible. And I'm not using impossible as the hyperbole, right? Oh my God, so impossible. No. This literally, you cannot anti-differentiate. There is no antiderivative of e to the x squared. It is a function whose integral does not exist. And you can prove that. Well, you can't prove it, but it can be proven that e to the x squared is impossible to integrate. All right, so don't think that e to the power is like the end all be all. They do tend to be pretty nice. However, there are some forms that are not just hard, they're literally impossible. All right, well, there's our e to the x, which now begs the, what about if we don't have e to the x? What if we have 2 to the x, 10 to the x, pi to the x, some other base? So let's see if we can build that antiderivative, or a rule for the antiderivative of a to the x. All right, well, let's see what we can do here. So we want now the integral of a to the x dx. I would kill for this to be e instead of a, right? Because if it's e to a power, we know what to do. Well, the good news is we can do some algebra to turn this into an e. We can actually write this as e to the natural log of a raised to the x. So this is just an algebra step. This is the fact that e and natural log, the natural log and the natural exponential function are inverses. So this e and this natural log would cancel each other out and would leave us with just a. Okay, so this is a property of logs and exponents. Again, go back and review your pre-calc if you're like, whoa, where'd that come from? But what this lets me do now, I can use the rules of exponents to multiply that natural log a and the x together, right? Taking something and raising to a power means multiplying those exponents together. Rule of exponents from way back when. All right, but now we can do a u substitution. Now we can do exactly what we want to do, which is let's let u equal natural log of a times x. And we're going to let all that stuff up top equal this. So then du is going to equal natural log of a times dx. Because natural log of a is a constant. That constant multiple goes along for the ride when we differentiate. And the derivative of x is just 1. All right, so I'm going to replace things. So that turns this into an integral of e to the u. Yes. And then the dx, if I replace that, that's du over the natural log of a. Right, just divide by the natural log of a. Now that natural log of a is a constant, so I can pull that out front. And if you look at what's left in my integral, not only is it nice, it's really nice. It's just e to the u. So we know that its integral is just e to the u. If I replace the u back in, or replace the u with the x's to get that back in, I get 1 over natural log of a times e to the natural log of a times x, which if I use that same rule of algebra to simplify this, gives me a to the x. All right, so again, I'm going to go ahead and box this because here is our antiderivative of any exponential function. You're going to get that same exponential function divided by the natural log of that base. And actually, if you go back and you look at the logs, remember when we did log base A? We got the same thing that we had for natural log divided by natural log of A. Same thing here. We're getting the same exponential function divided by the natural log of A. Cool. It's actually not that bad. We just have to remember to divide by that natural log. So let me show you an example here, because it is terribly easy. The most likely bases that you're going to run into other than E are 10, because our number system is base 10, and 2. 2 shows up a lot because things double, right? Like think about bacteria in a petri dish. Right? Bacteria actually reproduce by taking one cell and splitting into 2, right? So it doubles the number of cells. So those are the 2 that you'll primarily see. So let's do one with 2. Let's just say we're gonna, we've got a function, say, that we're integrating. Let's integrate. Actually, here's what we're gonna do. Let's do 2 to, let's have some fun. Let's do 10 to the x plus log base 2 of x. So we'll just combine them. So we'll have an exponential piece and a log piece. All right, well, here's how easy it is. So 10 to the x. It's going to give us 10 to the x over the natural log of 10. How was it? The log base 2. Well, that's going to give us x log x minus x divided by natural log of 2. And then, of course, to be good, we'll put on our plus c. All right, well, there you go. Okay, so check it out. We now know how to anti-differentiate all the 6 trig functions, any logarithmic function, and any exponential function. So we're getting there. We're knocking things out of this. Oh, we also know how to deal with polynomials. We also know how to deal with some rational functions, lots of them. We also know how to deal with some radical functions, right? Square roots. Like we're filling up the list. We're still not done, right? Obviously, there's still lots of other things out there, but we're getting there. All right, so any questions on the exponentials or the logs at this point? Maybe we're not quite ready for the questions yet. Still got to play with them a bit. Okay, so just so you guys know where we are and what's going on. So we just finished section 1.6. I think we're actually right on schedule, which surprises the heck out of me. But hopefully we keep it that way. On Friday, we do have our next quiz. I'm pretty sure the syllabus says that, so that's my plan. We're going to have our next quiz, and this one's going to be on sections 1.4 and 1.5. Okay, so Friday, we're going to have a quiz on 1.4 and 1.5. So really, 1.4 was just doing integrals, right? They call it the net change formula or something like that. Well, it's really just the fundamental theorem of calculus. Just thinking of it as we're adding the integral to our initial amount, net change. And then 1.5 was the substitution. So expect some questions about doing substitution with integrals, and then some applications like we've seen before about the total distance traveled, or total change in the account balance, or whatever all the other weird things that were in there. So Friday, starting at 8:30, go on to Canvas, download the quiz, work on it, get it uploaded by 9:10. And 9, 10, we're going to start in here, and we'll keep moving on. All right. So with that, I think I'm good to wrap up, unless you guys have any questions, anything you want to ask real quick before I stop recording. All right. Well, hey, with that, have an awesome couple of days, and I will see everybody on Friday. Cheers.
Thanks, Bruce.